Welcome to the Campus Energy and Sustainability Podcast. In each episode, we'll talk with leading campus professionals, thought leaders, engineers, and innovators addressing the unique challenges and opportunities facing higher ed and corporate campuses. Our discussions will range from energy conservation and efficiency to planning and finance, from building science to social science, from energy systems to food systems. We hope you're ready to learn, share, and ultimately accelerate your institution toward solutions. I'm your host, Dave Karlsgodt. I'm a principal at Fovia, an energy, carbon, and business planning firm.
We spend lengthy periods of time below zero. We'll sit there at 20 below for a few days at a time. So this concept of geothermal and 120 degree Fahrenheit hot water, it really was tested and talked about as far as can it handle the Minnesota winter. And we proved to ourselves and our leadership and even our engineers probably proved to themselves that this was going to work.
Well, it's good to be back as your podcast host again. Our last 3 episodes featured interviews from our guest hosts, including our summer interns. We have some more interesting projects in the works from Kaya and Sarah coming up over the next few weeks and months. In this episode, you'll hear an interview I recorded at the 2019 ASHE conference in Spokane, Washington. My guest is Martha Larson, manager of Campus Energy and Sustainability at Carleton College in Northfield, Minnesota. One editorial comment, we recorded this interview in the halls of the convention center, so you're going to hear a little bit of background noise. Our conversation focused on Carleton's ongoing transformation of their campus heating and cooling system. Carleton is in the process of switching from a traditional high-pressure steam system to a low-temperature hot water system using ground source heating and cooling as well as heat recovery technology. In my experience, the average sustainability professional does not get all that excited about steam pipes, chillers, and heat exchangers. When it comes to renewable energy, wind, solar, and batteries seem to get all the leading roles. I'm hoping this interview will start to change that perspective, or perhaps expand the cast of renewable energy characters at play. Martha is an experienced engineer, a thoughtful systems thinker, and a truly gifted communicator. She and her colleagues at Carleton are leading the charge on the types of systematic, transformational change we need to end our reliance on fossil fuels and create a carbon-neutral society that can work for everyone. Martha also is able to connect the dots on how this project aligns with Carleton's institutional mission, supporting a better working environment for their facility staff, and how she and her team were able to make the business case for such an ambitious transformation. I hope you enjoyed this October 22nd, 2019 interview with Martha Larson.
Well, I'm at the ASHE conference. I'm here with Martha Larson, and we're overlooking the Spokane River at the conference, and we are going to talk about steam to hot water geo-exchange at Carleton College. So Martha, it's great to be here.
Thanks very much, Dave. I'm happy to be here. Thanks for the opportunity.
All right, so can you just start out with just a basic introduction of yourself, your institution, and
Sure.
We'll go from there.
Yes, my name is Martha Larson. I'm the manager of Campus Energy and Sustainability at Carleton College. And I am the first person to hold that position. It was created in 2010. I came to it from a background in a degree in mechanical engineering, but really my career background was in project management. So wanting to move into environmental fields, it was a good match to come to Carleton and be part of the facilities department as a project manager, but also have the responsibility to build a sustainability program and an energy management program. So I now work there. There's an office of 2. I have a fabulous colleague, Alex Miller, who's our program coordinator. Carleton set a goal of being carbon neutral by 2050, and they did that when they signed the College and University President's Climate Commitment in 2007. In 2011, we did publish a climate action plan, and so that really cemented the goal and also did some quantified calculations on different strategies that might help us reduce our carbon footprint. So over the last 9 years, we've executed some of those, and some of them we've explored and dismissed, and then others, like the project we're talking about today, were not even really defined in our minds at the time that we published the plan. So it's very exciting to be at a place where we've now implemented quite a few strategies.
Yeah, it's not 10 years in the future, it's 10 years in the past now.
It is. It's hard to believe, but it's now 10 years in the past.
Very nice. Well, tell me just a couple of stats on Carleton. How big is it? Where is it? It's in, I guess.
Carleton College is in Northfield, Minnesota. It's 45 minutes south of Minneapolis, St. Paul. It was founded in 1866, so it's been around for a while, and it's a small liberal arts institution focused on high quality of teaching, high quality of education, and we have about 2,000 students, about 2 million square feet, And most of those students are housed on campus. So we consider ourselves a residential campus, and then that, of course, affects our energy footprint as well.
Okay, great. Well, let's talk about this project. When I was there in September, I was able to tour the power plant, and get a little bit of a history on how you guys have switched from more of a traditional steam system to geo-exchange, heat recovery system. So tell me a little bit about what's there, and then let's back into how you got to that system.
Right, so as of today, we just completed phase 1, which is we drilled 3 geothermal bore fields, 2 vertical, 1 horizontal. Those bores are about 510 to 520 feet deep, so they're quite deep. And as part of the phase 1, we installed a heat pump chiller that works off of the geo-exchange. We also retrofitted our East Campus buildings and our East Campus distribution piping. So the piping, we pulled out the steam, we put in hot water piping. And in the buildings, we increased the surface area of the radiation and changed out some air handling unit coils and other devices to run those buildings on 120 degree Fahrenheit hot water. Some of them had been native steam, and some of them were running on a more traditional 180 degree hot water. So lowering that temperature helped us optimize use of the heat pump for the east side. And then we have 2 more years where we will complete that transition on the west side. We won't get those buildings all the way to 120, but we will get everything to hot water, including the piping distribution, and then we'll upgrade our existing plant to serve the west side with the hot water system.
Okay, so multi-phased project, but you did the big part, because when I was there, it was a beautiful campus with people playing frisbee on top of fields and a soccer game going on, but underneath the ground.
Lots of piping.
How many boreholes did you guys?
300 total.
Wow.
Yeah.
Okay.
Yeah, about 100 of those, 94 were horizontal, and then the rest were all vertical. So we did make a big mess.
Okay, great.
And quite an adventure for a few years there.
All right. Well, so I love to geek out on these things, but I'm assuming some of the listeners may not understand all the physics fundamentals. So maybe let's hit a couple of those first, and then maybe we'll go into how you got this thing built, because that's a totally different story, I suppose.
Right. Traditionally, with our steam system, we put in steam in 1910, which is when we centralized our utilities with a central plant. And the electric grid wasn't very robust at the time, so steam propels itself through pipes. So you make 80 psi steam, and through pipes and tunnels makes its way out to the buildings. So that was traditionally how we did our heating. It was a completely decoupled system from how we did our cooling, which was to run chilled water loops through the buildings and bring that then heated water back to the plant, where we just exhausted the heat through the cooling towers. They operated independently. Now, by transitioning from steam to hot water and using a device like a heat pump chiller, we can take both of those loops, the hot water loop and the chilled water loop, into the heat pump together, where they exchange that heat. So all the heat we pull out of the buildings with the chilled water loop now gets dumped directly into the hot water loop. So we don't have to burn any fossil fuels, or the only electricity is pumping energy, and we get essentially free recycled heat. When we have too much heat, like in the summer, we'll put that down into the geothermal well fields, and likewise in the winter, we're able to draw that out. So for about 70% of our load, we're able to use the heat pump and the geothermal well fields to have an extremely efficient use of energy campus-wide. And then because we're in such a cold climate, we are supplementing, we have a hybrid system, so we're supplementing with high-efficiency condensing boilers for peak heating, and our traditional chillers that were already on site for peak cooling.
Okay, yeah, and I got to see the condensing boiler, which looks like a giant, computer. Basically.
Yeah, big metal box.
Yeah,
it's really a nice, clean little machine, and our maintenance staff is excited. The equipment is not too foreign to them. They understand a chiller, they understand a heat pump chiller, because it basically is very similar, and so I think they're happy that they're going to run a safer and a simpler system from now on.
From now on, instead of steam is a little more
quite dangerous, quite complicated. Yeah.
Right. Okay. Well, I've been joking with my uncle that if he went to school there and he wants to ever get his name on something, maybe he can't afford a building, but I suppose the side of the condensing boiler might be a place he could get his name if you gave the right amount of donation to the facilities
department. I thought
department.
about that. I wish I could sell a boiler, because that would be really fun to have a named boiler.
That's one of my dreams too. So yeah, we'll see. Anyway, we're talking about moving heat around then, instead of basically making it twice. Is that
correct?
A good summary?
Instead of throwing it away from the chilled water system and then making more for heating, we're just recycling it. You could think of it that way.
Great. Yeah, and when I was on the tour, I think with your colleague Fred, he mentioned you would even talk about like the heat and people giving off, like the students
Body
give off
heat,
lighting heat, all those things.
Computers.
You're capturing that now instead of putting it in the atmosphere.
Right. So all of that gets captured by the chilled water loop, and then again brought back to the heat pump, where it's dumped right into the heating loop. When we're balanced and we're using the simultaneous modules, our engineering team tells us that they can be up to 700% efficient. So a little bit of electricity to run the pumps, because you do have to move the heat around.
Okay.
1 unit in nets out 7 units out of power and work and energy, because we're able to use it for both heating and cooling just by moving it around.
And you defy the laws of physics because you're recycling?
Yes,
that?
we're just recycling it. So what we call an output is really just moving it from one place to another.
Okay.
So instead of having to burn more natural gas to create that heat, we just took it out of one building and moved it to another.
Great. Let's talk about how you put this system in physically, because this is not like, slapping some solar panels on a building
Right.
or even retrofitting an individual building. I mean, this is a systematic change for your whole campus.
It is.
What motivated you even to think, we should just rip up our whole campus and do this? Because I'm sure that probably didn't go over well.
No, it was a process. Yeah, and I will say Carleton has been very fortunate to have leadership right now that's very process-oriented, and they've reflected on where we are as an institution. And so it feels like our strategic planning right now is on very stable ground. It's based on really strong foundation. So in 2012, we did a strategic plan that basically said Carleton doesn't need to grow dramatically. We like what we are as a small residential college. And that led to a campus master plan that reflected those values and said, we're going to replace and renovate a lot of our 100-plus-year-old structures, even those are less old but not serving us well. And the focus of the campus plan, therefore, was on renovation, not, again, growth. That allowed us to then move into a utility planning phase that had a really informed amount of square footage for the next 20 to 30 years. So we didn't feel like we were shooting in the dark here. The goals of that plan were to plan for that campus, evolution that's outlined in the campus master plan. That was number one. Number two was to replace some equipment that was really at end of life. So major equipment like a steam boiler from the 50s, and we had some tanks and some chillers that were quite outdated, had, R11 refrigerant in them, things that needed to go away. And the third thing was to reduce operating costs and carbon emissions permanently. So those three charges merged into an evaluation of what would happen if we kept the steam plant and paid for the upgrades that it needs over time, and also continued operating it, because it's expensive to operate a plant that has to be staffed 24/7, 365. So that we looked at those capital and operating costs against a transition to hot water system. And we started by just saying hot water is the basis for all of this. That's the circulatory system. And off of that, we branched a few options, which were different sizes of geothermal, into different forms of this hybrid solution. All of that started with a concept study that was not drastically expensive. We did that with MEP Associates out of Rochester, Minnesota. And the concept led to a schematic design, because we said this looks promising. And we have good geothermal resource. We tested we did a test bore to check that as well. And then that schematic design, we did some cost modeling. We brought in a contractor to get market pricing, and our business office was very involved, our budget manager. So the cost modeling was holistic, and it reflected Carleton's rates that we like to think of when we do cost modeling. And all along that process, we got further and further into it till the point at which the board allowed us to release the base case and say we will not continue to maintain the steam system. We won't invest in it. It's not the technology we want for the next century.
Right.
And so at that point, we were really released to engage in a full construction document mode to go to the hot water. Approvals-wise and design-wise, we went into it with an iterative approach. Doing the construction, again, we phased so that we wouldn't be disrupting the whole campus at once, and we did most of the work in the summer so that our students could still have full access to all buildings. The well fields did trickle over into the fall, but we prepared the campus with some really strong outreach materials so that everyone knew what was happening and why our beloved quad spaces were closed off. Yeah, that was a big deal.
Well, and you did it between, isn't that where graduation takes place? So that's what Fred was saying, that you started the project like the day after. And then
we had to restore all the grass by the day of the graduation the next year, which was, it was a photo finish, I'll say.
That's good. Let me back up a second, because you said you got the board to agree that the base case was no longer your base case going forward. Tell me more about that. I mean, that seems like a critical step.
Right. So we had been prepping them with the concept studies, and I think at first, they were just sort of sitting back and going to see where this was all going to go. So I have to thank them for being open-minded enough to allow us to do a comparative study. And a lot of them are pretty savvy about potential for carbon taxation and just sort of impact on society. So they've honestly respected what we felt was our responsibility to show them multiple options. And then I think it really unfolded naturally into, there was a lot of the hard work was done really behind the scenes internally with our office, our engineers, Fred, our VP and treasurer, asking really hard questions and sort of anticipating what the board would need to know. Mm-hmm. And then when it went to our president, he too was very meticulous about questioning our assumptions. He questioned our cost modeling, and his advisory group was also present for all of those presentations. And so we had vetted it really well before bringing it to the board, and I think the board, they know that we do undergo these rigorous processes, and so they were also very trusting and open-minded when we presented our analysis to feel that they could trust that we had really vetted it before bringing it.
Feels like when I was on campus and just talking to your colleagues and staff, and that there just is a good working relationship amongst the staff. Like, I mean, people trust each other. It's a tight-knit group.
Yep.
You've done that. I'm sure similar processes you had to go through for those large capital investments.
We did. Yeah, we've developed, and I credit our leadership and our just campus culture with this atmosphere of trust, and I think that none of this would have gotten off the blocks, even in the concept stage, if we didn't have that mutual trust. I trust that my leadership, when they ask hard questions, isn't trying to criticize the work. They're trying to make sure that it's got integrity and that it will hold up.
It's the right answer for your institution, not you personally.
Right, and they trust me to be thorough with my evaluation and to manage the consultants really well, to choose the right consultants to begin with.
Right.
That I was fortunate to inherit a campus culture that was ready for a project like this.
Got it. Okay, because that seems critical to do something this big. Because you're essentially reinvesting in the veins of the campus, right?
It's the circulatory system for a cold Minnesota winter.
Right.
So everybody needs to be right.
Well, actually, just as a side note, so how cold does it get in Carleton? I mean, you're not Duluth, but it's not, or you're Bemidji, but it's not warm there either.
No, I mean, we spend lengthy periods of time below zero, and then with the latest polar vortex, we'll sit there at 20 below for a few days at a time. So this concept of geothermal and 120 degree Fahrenheit hot water, it really was tested and talked about as far as can it stand up to the Minnesota winter. And we also, another trust building exercise was to do pilot projects. So we did a mechanical renovation of our chapel. It was on its 100th birthday, so it had its 100-year-old air handling unit, which is sort of a awesome cast iron sculpture that we pulled out, and then we retrofitted that building with a radiation system that drew off of the 120-degree hot water. It's a combination air force and radiation. So by doing a building with literally no insulation except the roof, a 100-year-old stone chapel, we were able to test it even for ourselves and just say we did one building and that worked great.
Yeah, and that's a complicated building.
It's a complicated building. Yeah. It's an important building. It has irregular occupancy schedules. So it was a great test building. And so we proved to ourselves, and our leadership and even our engineers probably proved to themselves that this was going to work.
Okay, got it. So I remember I think I saw your presentation at the Second Nature Conference last February, and you talked about your own journey in understanding this systemically. So, I mean, you've got the pedigree to understand this, but there's a difference of that and really getting, I see how all these things fit together. And can you describe how you went through that process, and you and your team, because it wasn't just you.
It was me and my team. And so there are two concepts that we had to get our heads around. One was, how can it be that efficient? How can it be 700% efficient? And the other thing was, how can we heat a Minnesota winter, a whole campus, on 120-degree water? Which essentially, a hot tub is like 104. So we're not even that far off from something that you could actually bathe in,
Right.
So I think part of it was just having to step back and look at the formulas and the calculations and remember that there are concepts of physics and thermodynamics at play that have been tested, and there are, the formulas in the front cover of your physics book that still work.
Yeah.
and it's just that you need to look at what variables are at play and adjust them to meet the requirements. So as an example, our buildings with the radiation at 180 degree hot water, usually there's a radiator under the window, partly because that's enough to put out enough BTUs, and also it looks nice to be centered under the window. The engineers basically did calculations room by room of how many BTUs were required to heat that room, and then how much more radiation, how much longer that radiation would need to be to get the same number of BTUs. So it's a lower temperature water.
Lower temperature, more time. But
more surface area.
You still get to the same temperature.
And you still get the same amount of BTUs. And so theoretically we sort of got it, when we had to slow down and just think about it practically. And then we had to think about in our buildings, each building was different. So some buildings have radiation, so that had to be upgraded. Some buildings have forced air, like fan coil units. So, how do we do it with fan coil units? With each air handling unit, there's different sizes and configurations. So how do we get bigger coils in the old units so we're not replacing air handling units? And in each case, the engineers had a slightly different solution for each building. It's quirks. And each time they figured it out.
They were probably excited to get a chance to figure it out.
It's a puzzle. It's a puzzle. And then, of course, the chapel project proved it to us in practice. Because everyone wants to believe the calculations, but there's still something a little unnerving about just believing something on paper. But as we've gone through, now we've done 10 buildings that retrofits, and so it's really, we're quite comfortable with it now, and we're comfortable with the fact that each building is different. It's not going to be a cookie-cutter solution to make each building work on this 120 water.
But neither is your steam system, I would suppose, right?
Each building was different
to begin with,
yep,
right?
Differently designed, so it's very easy to equate that. And then on the efficiency side, we just really had to, again, go back to the idea of just heat transfer and the fact of the refrigeration cycle, and just remember that this is just evaporators and condensers and like compressors. It's all the things that you have in a refrigerator or even a window box. If you have a window air conditioning unit, it's spewing out heat out the back, and if you can just catch that heat and direct it through metal plates or fins. So again, it's just going back to the things we know theoretically and reminding ourselves that you use those really tried and true formulas.
Right. Yeah.
Figure out the solution.
It's been interesting for me to think about, like an air conditioner, like you said, it's spewing out heat, and that's its function. So we never think of that as a waste product. If you can capture it, then it's a resource.
And it's an input.
Right. Yeah.
Exactly.
No, that's great. And I know the other thing that I've learned is the idea that you don't need to burn gas, which is what you probably know, like 1,500 degrees or something when it burns.
Yeah.
If you're trying to get 100-degree water, like that's a little bit overkill, right?
Yep. Yeah, to make steam, we have to combust something. When we looked at biomass and we looked at high heat content wood pellets as sort of a manufactured product that would be a reliable source, it was 8 semis a day to do the campus in January. So we thought about truck emissions, truck traffic. We thought about warehouses to store this stuff, keep it dry. Right. We just couldn't imagine operating a facility that way. So geothermal was a light bulb moment for us. We'd thought about it for a building, like a data center where we have cooling loads all winter. Maybe we can have this balance and pick the right building. But then MEP Associates did a presentation on Ball State University, which was using the diversity of their campus to balance. And that was a light bulb moment for us. So that's what really started our relationship with them, was having them come to talk to us about district energy as geothermal.
Because you're not just running air conditioning in the summer and heating in the winter. We're doing
cooling
both all the time.
Right. So we always have a way to exchange energy.
Right. So then it becomes like one giant building rather than...
Exactly.
Okay.
That was a really defining moment for us to think about geothermal. And it's true. If you make steam, you have to heat the water to 330 degrees to get 80 psi. You can never do that with solar panels. You can never do that with heat pumps. You can't use condensing boilers, which are 95+% efficient.
Oh, how hot do those get? What?
Those are really looking for a return water temperature that will allow those vapors to condense. So you get a little extra boost of efficiency by using both sensible and latent heat. All those great technologies to move heat and to make heat are really built for hot water.
Got it. So you can't use a condensing boiler if you're making steam,
right.
essentially.
It just won't work that way. It won't condense. And so to engage in the future of heating technologies, we just also felt like having the right circulatory system. The equipment can come and go. We can get more efficient equipment. We can get the new technologies in a few decades when our heat pump poops out. But to have the hot water as the circulatory system is the key to unlocking our access to those technologies.
Got it. So this is an enabling project,
not just for today, it's for the future. Yeah.
Okay. No, that makes sense. So I know that there was a point at which your project got a little bit accelerated because there was a science building that had all of a sudden was coming online and gave you an opportunity to maybe move things more quickly than you had otherwise planned to do. Can you tell me a little bit about that part of the story?
Yeah, that was sort of a fortunate coincidence, I would say. The two projects were operating in parallel. As part of the campus master plan, there had been an identification that we need to invest in sciences and upgrading our science facilities. And that became a real focus of our fundraising efforts and our president's sort of call to action. So that building was going to be we have 3 buildings built in a horseshoe shape. And initially it was going to be sort of a 4th addition to that complex. But as the design evolved, they decided to take down one of the buildings that wasn't functioning quite as well for our purposes and then replace it with the new third leg, essentially, of the science complex. And our engineers recognized this as a real opportunity to piggyback on a construction project that was already planned. They're already digging a basement for the science building. If we go one level further, we could build a sub-basement to house the new equipment, because we can't take the old equipment offline until the new equipment is constructed. So we actually had to accelerate the progress of our utility master plan design to marry that construction of that energy station with the construction of the science building. So I think it was a good catalyst for us. It was a little stressful at times to have to fast track, but it allowed the college to get more bang for our buck and to also put this station in a place that really works well for the campus. We didn't think people would be excited about placing a new facilities building in the campus landscape. So this really tucks it right nicely under a building that...
And it's really close to the one field, if I remember right?
The other thing is, it's right on access with all three well fields. So we were able to have the shorter runs of the large piping that goes back to the energy station.
Right.
It's really convenient. And also the science building is the highest energy intensity on campus. So
no distribution loss if it's in the same building.
Right,
Very
it's
little.
just right there under the building.
Oh, that's cool. Yeah, it was one of the cleanest mechanical rooms I'd ever been in, I have to say.
Thank you. Yeah, we're excited about that.
I know it's brand new, but still.
Brand new.
I also appreciated all of the charts and graphs and visuals that you'd pasted up for the tours, which maybe leads me into my next question, which would be, you had to basically convince the board, we're going to change out the circulatory system for this campus. We're going to spend a lot of money up front to completely change the future, and you can phase it, but I know what Fred had said is you can't do part one if you're not going to commit to part two. So tell me a little bit more about the journey of bringing along your financial oversight team. I guess that would be your board, your CFO, the president.
Right, so how we thought about that. Well, really, for us, there's more efficiency with going to hot water. Of course, more flexibility for the future, modernizing a 100-year-old system. But in addition, we had to make cost model, a convincing case that we weren't just squandering money for sustainability alone, or even for facilities upgrades that could be perceived as not necessary. But our operation of the steam plant is quite expensive because, again, in Minnesota, the laws are fairly strict about high-pressure steam plants needing to have eyes on them all day long, 24/7, 365. So we have people working Thanksgiving Day, they're working 2 a.m., they're working on the weekends. And most of the savings are coming from reduction in those maintenance and operations costs.
Not the savings of energy.
Yeah, the energy savings, frankly, we are saving about 40%. We expect our energy use to go down by about 40% because of the recycling of the heat.
Which is not insignificant. Yeah, that's amazing.
But the utility cost, given that we're now moving away from natural gas to electricity for the heat pump, electricity is more expensive per BTU. Right. So the utility costs will go down maybe 8 to 10%, but the operations costs will go down maybe 30%. And that's both the repair and maintenance of steam systems, which is just more complicated, but it's also, we'll now have an 8 to 5 staffing model with on-call nighttime monitoring. So it's a better work environment for people to not have these changing shifts and working nights and weekends, and it's also a more economical staffing plan for Carleton.
Right. If you had to order it, it would be the maintenance, the actual physical cost.
Operation and maintenance first.
And then the labor, then the energy savings, maybe? Is that?
Yeah, it would probably be labor first. Okay. And then kind of the combination of maintenance and energy utility cost savings.
Got it. Okay. Yeah, that's something that's taken me a while to get around to. Just there's only so much money you can save through energy because it costs a certain amount. Mm-hmm. That's it. You can save that much, but if your system costs more than that, then how do you justify it? But we forget about. Oh yeah, you still have to run the system.
Right, yeah, there's a long-term savings of the operating costs. By doing the new system, there's an upfront capital cost, which is financed, but we will be able to pay the financing annually with the avoided cost.
Right.
So it worked well into our cost model, and then in about 18 to 20 years, we feel like those two systems break even. The incremental cost of the new system breaks even with operating the old one, and from then on, it's just more savings and also flexibility and opportunity to utilize a more modern system.
Right. Okay. Well, and this also has the effect of electrifying your system. People throw that term around, right? But that's basically what you've done, right? You switch gas for pumping.
Yep, exactly. And that's something we came to again. That was one of our realizations through the process because people weren't using the term strategic electrification when we started this process. But we ourselves realized as we looked to the future, what would we do? How will this play into the future of our goals? We realized that electricity is really where you can get really accessible renewables. And we own 2 wind turbines. We have solar PV. We have solar thermal. So we really are familiar with how to make renewable energy. So it became clear to us that coupled with the fact that our utility company has committed to being lower carbon and carbon free by 2050.
So all of your electricity sources are getting greener in every way, like your own production on site, your utility, the country at large. So that makes a lot of sense. So you haven't completely gone away from gas, right? You're still using gas in the condensing boilers,
Correct.
which is like for really cold
peaking.
days.
Yep.
So, okay. I assume you still have Bunsen burners in your labs.
We do.
Stuff like that, which is negligible, I'm sure. But you're still using gas. Are there any other things has this precluded you from running any system that you would otherwise, from your steam system? Are there process loads you needed to deal with? Or
Yes, correct. Yeah, that was part of our thought process. And so we had to look at each of those individually. Certainly we have steamers and kettles in our kitchens, and we have boosters in our dishwashers, and so each of those had to be brought to more of a local source. Usually it's an electric sort of steam generator to serve those loads. We had autoclaves that thankfully were already local to the building, which I was worried about them until I realized, they're already taken care of.
Oh, you thought they were running on the steam system, and they were actually running. Okay.
They actually had their own source. And then the one area I think where we really got innovative was hot water. We had steam bundles in heating hot water tanks in our dorms and our buildings just to create hot water for showers and faucets, but also the pools were heated with steam bundles. So as part of this, we had to think about how to deal with that. And one thought was, let's put little natural gas hot water heaters in each building, which then marries us to natural gas.
Right.
Not to mention there's an architectural complication with routing a flue out of these buildings without really disrupting floor plates. And all of that was expensive. So we started to challenge that and say, isn't there a better way? And our engineers came up with the idea of a plate and frame heat exchanger, whereby the 120-degree hot water will pass by one side. The domestic hot water loop will pass by the other side. And we can get the domestic water up to about 115 degrees Fahrenheit.
Just to treat heat transfer from...
Just by heat transfer, yep. Yeah. And so that was one area where I felt we made a real breakthrough, because the pools especially are an area that we are heating them year round. And so all summer when we're pulling heat out with air conditioning, the pools are going to suck up.
And that prevents you from getting out of balance to some extent.
It does.
Right?
It helps the summer loads be a little more balanced. So that was one of our areas where we really had to take a step back and say, why are we marrying ourselves to natural gas? Why would we localize all these little domestic hot water systems? Now the fact that we've tied them into the more district energy system approach just emphasizes really wherever possible to get to a systems thinking approach for all these little details.
So you basically hooked up like your pools and these hot water heaters into your circulatory system that you've now built.
Right. Yep.
Yeah. Is there any cross-contamination risk there?
They're separate loops. So they really are. There's 2 pipes that come in, in and out, supply and return for the domestic side, and then there's a separate supply and return for the heating hot water. And the side benefit was all these big, huge tanks, some of them are the size of a small school bus in our dorms, they got to come out. And now we're not holding water, and there's not, kind of crud gathering in the bottom.
And they're not going to break and flood the dorm.
Yeah, they're not going to flood the dorm. They're not, they were coated with asbestos insulation. So that sort of whole feature just went away.
And those are probably things you didn't have in your cost model at the beginning, right?
Right. I mean, that's a benefit that just came out of the project that we're now experiencing as sort of a bonus.
That's cool. Yeah, liquid that goes down into the geothermal wells. Let's talk about that, because there may be some concern of like, if you're drilling holes in the ground, are you fracking, or you'll hear people that will say stuff like this. But there is some risk, like you can get into the water table and things like that. Talk to me about.
Sure. Yeah, that we talked about that quite a bit. The liquid that we're using is just water. So our whole distribution, including the geothermal loop, is water. The only thing it has in it is some biocides, which just prevent growth of algae and stuff like that. But it's things that are not. It's not refrigerant.
Okay, so it's not going to leak, and you're not going to
Right.
blow your savings by releasing some refrigerant in the atmosphere.
Right,
okay.
right. And furthermore, the wells, that's basically a piece of maybe a 1 1/4 inch tubing that goes down and forms a U at the bottom, and that whole thing is encased in concrete. So the whole well is about a 6-inch diameter. That U-bend gets inserted down into that well, and then it gets
pour concrete on top of
filled
that.
up with concrete, right? So it's pretty encased in that. Each well is fairly well
And if
encased.
it leaked, you're leaking water. Yeah.
Correct, yeah.
Got it. Okay. And then because I suppose that concrete then prevents the different elevations of the water table from interacting with each other or stuff like that.
That's right as well. Yep, and we did have to get permits from the Minnesota Pollution Control Agency. We also had an alum, thankfully, that was working for the Minnesota Geological Survey and just was really familiar with the geology. So between that alum and our professors and the MPCA, kind of all looking at this together, we were able to get our permits approved.
To get that, okay. And I suppose one thing we should talk about, we missed it in our physics discussion, how does that actually work? How do you use the earth?
How do you actually use the earth?
Describe the physics of that, because it's not the most straightforward.
Well, and the fun thing about this was our geologists challenged the engineers on this. The engineers do a test bore, and they get the different types of geology, the stratigraphy as you go down, and then they also run liquid through it, water through it, to get some conductivity values.
Okay.
Engineers plug those into a computer model, and there's modeling software specific to projects like this that will tell them how much linear footage of geothermal well they need to marry up with the tonnage of heat pump that is sized for our campus. The geologist said, well, that's not a static value because groundwater is going to affect that, and it's flowing, and it's going to be, different temperatures and different volumes depending on the seasons. And the engineers said, well, yeah, but we don't have a number for that, so we can't put it in the model. And the geologist said, well, you're being way too conservative because the groundwater is going to make the heat transfer way more efficient than what you can assume with a static model. In the end, they agreed to disagree that the modeling, was the best that it could be, and they designed the well fields to that model. The geologists had to concede that it might be more well field than we need. And now what we've done is the geologists put in 5 of the bores in our main quad, they put a fiber optic cable that they basically attached to the U-bend and sent it down 520 feet, and they can get temperature readings from 520 feet to surface. So they're going to study what they can learn from that about groundwater flow, groundwater volume, and temperature, while we marry that up with the data from the well fields that we're getting through the building automation system. And we'll just kind of see empirically what we can find out about the effect of groundwater flow on the efficiency of the bore fields.
And let me see if I can understand that. Like in the winter time, you're trying to get heat. You're running cold into the earth, and then the earth would heat it up. But if you keep doing that too long, eventually, like sitting on a park bench, the heat transfers and it kind of equalizes, so that becomes less effective. But if the water's running through,
it's sort of refreshing it. It's like a battery that's constantly being refreshed.
Okay, no, that's great. So,
and the ground for Minnesota is about 50 degrees. From below the frost line down, it's a consistent 50 degrees, 51 to somewhere in there. So when you're in the wintertime and you're sending, you've sent your water through the buildings and the heat has transferred into the buildings, the water comes back colder than that, like maybe in the 40s.
Okay.
So it's going to go down to the earth and get preheated before going through the heat pump. The reverse in the summer, we send water down that has sucked all the heat out of the building, so it'll go down and it'll be above 50 degrees. Okay. So it will get pre-cooled. So the magic is Earth's temperature is perfectly situated between where we need it to be in cooling heating season and where we need it to be in heating season.
Okay.
So it's always helping us to preheat or pre-cool. In addition, if it does store any in the bedrock there, that can act like a traditional battery where it's gaining heat in the summer and then releasing it in the winter.
And that because you're doing it both seasons, it balances out.
Right, basically. It balances, and we'll watch that over time, and we'll kind of optimize our system to not overheat or overcool.
And then you can supplement with your other systems.
You can always supplement, which is part of what we liked about the hybrid system was the ability to really trim that operation.
Got it. Okay. No, that's great. That's helpful. All right. Last line of questions is more about you personally, because you're not maybe the traditional engineer. Just tell me a little bit, how did you get to this space?
Yeah, I always liked puzzles, and I liked, I was good at math, and engineering was a good fit for me, but I also liked music, and so I ended up at Northwestern University because I had strong engineering, strong music, but I pretty quickly realized that, I had to pick one or the other. It was going to be hard to focus on both and do well, so I picked engineering as the more practical solution. When I got out of school, or as I was in school, I realized I actually went into acoustics because I realized there was an engineering field related to mechanical engineering, designing buildings that are built for musical performance, theater, etc. And so I started with Kierkegaard Associates, which is a pretty prominent acoustics firm in Chicago. I had done an internship with them. And it got me into the world of construction and design and big buildings. And so I learned about how large projects happen, how fundraising happens, the fact that they have an owner's representative and a project manager, as well as architects and acoustical consultants, and so I really got ingrained into the construction industry through that first job. And then with acoustics being such a narrow field, I moved to project management. I worked for a company called the Rise Group, which was doing large municipal performing arts art museum projects. And my last job there before moving to Carleton was the St. Louis Art Museum expansion. So again, really complicated projects with a big team coordinating a lot of people. And in that role, I was an owner's representative. I was assistant project manager.
Okay.
There was a senior project manager who mentored me. And I feel like that really gave me my project management chops, because those were stressful jobs, big jobs, lots of stakeholders. And so coming to Carleton, I felt prepared for the complexity of the projects, but it was just the focus on environment was where I wanted to move with my career. Just knowing the crises that are rising out there, I feel like it's all hands on deck. Everybody needs to be working on the environment right now.
Well, I hope that people listening to this episode will appreciate the diversity of your background, putting the puzzle pieces together. You have a grace about the human side as well as the engineering side, and it's just really, I'm in awe of hearing how you've put that together. I see so many projects that don't have that approach, and it's I think that's a testament to how you guys got this done. So.
Well, thanks, Dave. Yeah, it's always about people too, and communicating what you're doing, not just barging in and building something.
Right, yeah, exactly. No, and well, maybe then I'll leave that as the last question. Tell me more about how you're communicating this project out to the world now. I know I've seen there's maybe some charts and graphs that we can share on the podcast website. Sure. How much time do you spend talking about it like this?
Quite a bit, actually. My colleague Alex Miller and I spent a lot of time. We hired a graphic designer to help us with our charts and graphs. We did a lot of dorm outreach. We did a lot of communicating with the campus community before, during, and after the project. We've done a lot of presentations at conferences because our goal is to keep our campus community informed and appreciative, and also just to be able to celebrate with us the big accomplishment that Carleton has achieved. And it's also to help others who are following in our footsteps not have to deal with, basically let them benefit from our lessons learned. Is the point. And
they don't have to be the first one in Minnesota to do this, because you've already done that.
They don't have to be bleeding edge. And we'll learn from them too, because each one is different, and each institution is going to take a different approach and have different tweaks. But that's very important for us to make sure that everything we've learned, we'll put it out there so that more projects like this can be constructed, and we'll all learn from each other.
That's great. Any big new projects on the horizon? You guys have a flux capacitor in the works, or?
The next big idea is always the question that's on my mind. Well, I figured we'll get 2 years left of phase 2, but I certainly am thinking about how we're going to provide that electricity renewably. So I think renewables behind the meter is really where my mind is at right now.
Very good. Well, maybe in a couple of years we'll come back and talk about that project.
Sounds great.
All right. Thank you very much.
Yeah, thanks, Dave.
Yeah.
Well, that's it for this episode. In addition to Martha, I wanted to give a special thanks to Carleton's VP and Treasurer, Fred Rogers, who led the tour of Carleton's district energy system during the UMAX conference in September, as well as my colleague Kaya Findlay, who edited and produced this episode. You can find more information, including photos of the geofield under construction, at our website at campusenergypodcast.com. If you want to keep up with this podcast, you can follow our page on LinkedIn. We offer this podcast as a free service, but if you'd like to support the show, please share it with your friends and colleagues, or take a minute to write a rating or review on iTunes. As always, thanks for listening.